Okay, example 3. With the help of your calculator's ability to graphically find zeros. This is one of the big 3 things that we're going to be doing with our calculator this year. We're going to be finding zeros for equations that we're trying to solve. We're going to be trying to find numeric derivatives and later on numeric integrals. We can use it for a whole lot more than that, but only on the portions, bless you, that are designated for a calculator. Is this one such section? Yes. So if you have your calculator, feel free to get it out. If you have your little Wabbit Emu emulator on your smartphone, that works great as well. Otherwise, you can borrow one of mine, or you can just watch along up here, because I'll be modeling what we're doing. If you have one, it would be okay to kind of travel with it, because we're going to be using it intermittently from here on out. We want to find all the values C that satisfy the conclusion of the mean value theorem, not the EVT, but the MVT, for this function on that interval. Now, number 1, does the MVT apply? Don't assume anything, right? Because when you assume something, you got 3 fingers pointing back at you. That's a mixed metaphor. We have a what kind of function? Polynomial, which is continuous and differentiable. Where? Everywhere. So including continuous on the closed interval that we're given from -1 to 2, and differentiable what? It only has to be differentiable where? On the open interval, possibly in France, but it doesn't have to be differentiable at the endpoints. Okay, sweet. So the MVT applies. So we're guaranteed at least one x value where the slope of the tangent line equals the slope of the secant line. Good. Where f prime of x equals the difference quotient. Yeah. So here's what you do to get points for your setup. Your function's name is f. See it? You're going from x equals -1 to x equals 2. Here's what you write. You put f prime of x equals f of 2 minus f of -1 all over 2 minus -1. Show f prime the derivative, and you show the difference quotient. Make sure it's a quotient of 2 things being subtracted. All right, now you can go ahead and specifically find each of those. F prime is pretty easy, 3x squared plus 4x minus 1. And then from here, you want to be a little bit careful because the function looks manageable, your x values look manageable. Do you want to plug in f of 2 and f of -1 on your own, or do you want to use the calculator? Plugging into 2 is not bad. Plugging into 1 is not bad. I'm going to show you how to use the calculator because sometimes you're given a function that is really, really ugly, or you're given values of x that are ugly. If it's a calculator section, chances are you want to use your calculator. But in this case, you have the option. So in y1, I'm putting x cubed plus 2x squared minus x. Okay, now here's the important thing. When you call it y1 in your calculator, it's not a bad idea to come here on your paper and label it as y1. Because you're going to have lots of things entered in y1, y2, y3. All right, so now that you have it in y1, and you double check that you got it in there correctly, mine looks good. Now you can go to the home screen, and you could just put your difference quotient. Alpha 1 or alpha y equals numerator over denominator. So here we go. F of 2 is going to be the function value, which you can find under the alpha trace menu. There it is. It's in y1. So you put of 2 minus, do it again, bless you, of -1. Now on the bottom, of course, if you don't want to put 2 minus -1 type in, I get it. That's one you could probably handle on your own, right? 2 minus -1 is 1, right? Right? No, it's not. If you think you're going to mess up, just put 2 minus -1 and let the calculator do it for you, right? So you get 4. So it turned out to be pretty nice. All right, so I like getting down to this step because I see the average rate of change. This cubic polynomial, as we move from x equals -1 to 2, goes up, increases on average 4 units vertically for every one it's going to the right. So from -1 to 2, that's going to be up 4 over 1, up 4 over 1, up 4 over 1, on average. Does that mean it was going up the whole time necessarily? No. And does it mean that it was going up at that pace the whole time? No, that's just its average. Now we want to know for what value of x on the open interval from -1 to 2, the derivative equals that. So now we solve this. How do we solve equations on our calculator? What would I recommend? Get everything on one side, set it equal to 0. Always. You could have graphed the derivative in y2. I don't know why it's 8. Make sure when you bring it across, that you bring it across carefully. How's that? For some reason, I just wanted to make I don't know. I have no idea. I warned y'all before I started. It's one of those days. But I'm doing so far so good. Just one. You keep track of them. 1. You don't have to keep track of them. You will. Thank you. Okay, so now I got rid of my function. You could keep it in there and then graph the derivative in y3 or whatever you want to do. But because I'm going to be using my graph, you either get rid of the old function or you turn it off by clicking enter on the equal sign. So here we go. 3x squared plus 4x minus 5. And now I'm not calling this, I called the function y1 earlier. I got to remember that this is now the derivative. So here's what we do. Instead of hitting zoom 6 is not bad if you don't know what the graph looks like. But I kind of don't want to do that. So I'm going to hit enter. Oh, it's a parabola. I kind of knew that. I am interested in finding the values guaranteed by the theorem, which is from -1 to 2. So here's what I would recommend always. If you're given an interval, put that for your x min and x max as well. What that does is it keeps you in the zone, right? Prevents you from being tempted by other x-intercepts outside the interval. You don't want to be tempted, even if you have a high emotional quotient. Now, -10 to 10 is good. It puts the x-axis right in the middle. But I'm going to go ahead and go from -3 to 3. Small but symmetrical. That's what I say. Now, are we guaranteed an x-intercept in this interval? Yeah, the mean value theorem guarantees there's at least one x value where the tangent line is equal to the secant line slope. And, well, we could have more than one, but we're guaranteed one. Okay, so here comes the derivative with the -4 or the -4 added to it. And there's the y-axis. So the reason that I sketch y equals 0 and y2, I just kind of keep it in there, is because it's a lot easier to find points of intersection. Second trace number 5, and now you just go enter, 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 and it should find it for you. So notice it's an ugly decimal. You do have to write it down. So you'll say underneath there x equals 0.786, and you can round or truncate. Now, just kind of an FYI, anytime your calculator finds something on the graphing screen, whatever it called x there, it's going to store as x here. And if you hit alpha 1, that's where the y variable is, it also stores the y value that it just found there. And later on, we might be interested in using those. The x value is especially important because it doesn't terminate. It's an ugly decimal. So if we had to find another one, here's where I would say let x be stored. Right above the on button is store. And then call it alpha A. And now it's locked in at A. So now I can go back to my graphing screen, find another x value, and I still have all the decimals I need. Okay, one last thing, I guess. If you do call it A on your calculator, it's okay to call it A here. Just say A equals X equals the number. You still need to report 3 decimals. But you never use that rounded number for a subsequent calculation. Yay, we're done with 3. That one was with the calculator. Any questions on that? All right, it's important to remember that you need to be looking on the interval that the mean value theorem guarantees, which is what type of interval? Open interval. Okay, so I mentioned this the other day that sometimes College Board is going to give you a problem where one of the solutions is not just outside the interval, but one of them is actually an endpoint of the interval, and you need to know not to include it if it's asking for the values guaranteed by the theorem. Like example 4. Determine if the MVT applies, and if so, find the values guaranteed by the theorem. Well, once again, we have a polynomial and a closed interval. So does the MVT apply? Yeah. So let's go ahead and set it up, same way as before. F prime of x is going to equal f of 3 minus f of 0 all over 3 minus 0. There's a check. Beautiful setup. Now this one's a no calculator, so we got to go solo here. 3x squared minus 6x plus 2 equals, and plugging in carefully, of course, we get 3 cubed, which is 27, minus 27 plus 6. Nice. And then minus 0 all over 3. So again, I like to keep everything intact until I get down to a number on the right. We're going to end up with 2. So notice what that means. That means that the average rate of change of this cubic polynomial is 2. As we move from left to right from 0 to 3, on average it goes up 2 over 1, up 2 over 1, up 2 over 1 to arrive at its destination. Didn't have to go that the whole time. Didn't even have to be increasing the whole time. That's just its average. But what we do know is that the derivative should equal to at least once between 0 and 3. So we can find the value now. What happens with your 2's on either side? They cancel. And we're left with 3x squared minus 6x equaling 0. We could factor out a common factor of 3x, and we're good. We get x minus 2. So we get x equals 0 and x equals 2. And without a doubt, 100%, the cubic polynomial has 2x values where the slope is 2. Okay? The cubic polynomial has a leading coefficient of 1 and 2 horizontal tangents. So it's going to look something like this. And we actually know that it's going to equal a slope of 2 different places. Those are the horizontal tangents I drew on there. But I can maybe imagine that it's going to be 2 right here. And if it's going to be 2 there, then it'll be 2 somewhere else, maybe right there. Yeah? But remember, we are looking for the places where it's equal to 2 strictly between 0 and 3. And are 0 and 2 both strictly between 0 and 3? Well, 2 is on the open interval, right? But what's wrong with 0? It's an endpoint. Does the mean value theorem make allowances for endpoints? No. So this is where you have to know that the theorem is looking for just the values strictly on the open interval. So 2 is the only answer. And if this were a multiple choice question, there would be an answer choice that has both 0 and 2. So again, it's more obvious to throw them out if they're outside the interval. But for the mean value theorem, if the value shows up as an endpoint, you kick it out. Now, having said that, we're going to have 4 VT theorems this year that we learn. We've already seen the IVT. We've already seen the EVT. Both of those make allowances for the value that you're finding to actually be at the endpoint. It's only the MVT that says it has to be on the open interval. So you kind of have to remember that. The 4th VT theorem is actually another mean value theorem, but it's going to be for integrals, and it's going to also allow endpoints. But this MVT does not. Very important. And there's an example that will work after lunch that will help you maybe remember that if you have a hard time remembering that. Hopefully y'all don't have a hard time remembering that. MVT is what? Looking for a value on what type of interval? Open or closed? Open. Yeah. Okay, good. Very quickly, example 5a. On these two here, we want to see if the MVT applies or doesn't apply. And if it applies, we're going to find the value guaranteed by the theorem. Do we have a polynomial? No. We have a rational function. Look at the denominator. What value is not in the domain? 1. Is it going to be a vertical asymptote or a whole? Just a review question. VA, good, because when you plug a 1 to the top, you get 6, and 6 ain't 0. So we have a vertical asymptote at 1. That's the only place where that function is not continuous and therefore not differentiable. Is that going to be an issue? What interval are we trying to look at? -3 to 5. Is 1 in the... Yeah. So here's what you would write. the MVT does not apply. MVT does not apply since f of x is not continuous on the closed interval from -3 to 5. You could say not continuous at x equals 1, epsilon -3 to 5. That wouldn't be wrong, but you don't have to. Okay? You want to speak specifically to the theorem. Could you also say it's not differentiable on the open interval from -3 to 5? Would that also be a good justification? Sure, because it isn't differentiable. But if you talk about differentiability, make sure you put in the open interval. Because again, you're trying to show knowledge of the theorem itself. We'll squeeze this one in before lunch. What are we on before lunch right there? Fractional exponent less than 1. Cuss flirt, cuss flirt. Cuss flirt. We know that the value of x that makes this factor 0 is going to be a cusp, right? What value of x is that? 0. Is 0 in our interval? Yeah. Now, what's the reasoning? Is it continuous on the closed interval? Yeah, because that's just the cube root of a number squared. Its domain is all real numbers, so it's continuous on the closed, but it's not differentiable where? On the open. So the MVT does not apply. Does not apply since hasty make wasty, here we go, since g of x is not differentiable. Ooh, that's a big word. We'll abbreviate diffable on the open interval from -3 to 3. And of course, that's also one of your new parent functions, right? X to the 2/3. Which one is that? That's the cusp. That's the bird graph, right? That's the absolute value of x graph that stood out in the rain. It was like wilting. It'll be due, today's Monday, it'll be due on Wednesday. Yeah. But we'll quiz tomorrow over EVT and MVT. Sound good? All right, when you come back, we have a pumpkin problem. Everything these days is pumpkin spice, pumpkin flavored. Even the calculus problems are pumpkin flavored. Have a great lunch.